In the late 1980s, the city of Boston embarked on an ambitious project. It was called the Central Artery Tunnel Project, but it would become known as the Big Dig. The goal was simple in concept yet monumental in scale: to dismantle an aging elevated 6-lane highway. Replace it with a state-of-the-art depressed central artery, 3.5 miles of underground highway. This engineering marvel was meant to unclog the city's chronic traffic congestion, reconnect neighborhoods long divided by the intrusive steel artery, create acres of new urban green space. The initial budget, set in 1985, was $2.8 billion. By the time final major construction concluded in 2007, the story had changed. The project was hailed as an urban planning success. Yet the final price tag had ballooned to $14.6 billion, not including interest. This represented a cost overrun of more than 400% from its original estimate. The Big Dig became a national symbol of a common problem. Big projects often cost more than promised. This is a story of a system, not just a single project. The pattern repeats across the globe. High-speed rail lines, international airports, Olympic stadiums, power plants. We see meticulous plans and detailed spreadsheets. We hear confident assurances from planners and politicians, yet the numbers grow and timelines stretch. The public is left wondering how the initial calculations could be so wrong. We live in an age of powerful data and sophisticated project management, yet we can't predict costs. The easy answer is to point fingers: optimistic planners, greedy contractors, meddling politicians. These explanations offer partial truth, but are ultimately unsatisfying. A more complete explanation lies deeper, in the system. Look past individual actors and examine incentives, feedback loops, and human biases. This is not a story of blame, but of understanding. We will explore and map the hidden architecture that produces cost overruns. Let's begin by having a look at the entire system overview. First, the cast of players, mapping the project ecosystem. Second, the flow of a project, from idea to reality. At its core, any large infrastructure project is a temporary organization, a complex web of distinct groups brought together to achieve a single monumental goal. To understand how costs spiral, we must first map this ecosystem and identify the key players: planners, funders, regulators, contractors, users. The process begins with the planners and sponsors, government agencies, public authorities, private consortiums. They are the visionaries. They identify a public need: new bridge, faster railway, more efficient power grid. They define scope and champion benefits, securing initial political and public buy-in. Their role is to set the stage and show feasibility. Once the vision is established, the funders enter: national governments, state or municipal bodies, private investors, international development banks, gatekeepers of capital. They assess financial risks and potential returns. Funders rely heavily on the initial cost estimates and benefit analyses provided by the planners. Their decision to release funds is a critical milestone, transforming an idea on paper into a live project with a tangible budget. The flow of money from funders to the project is the lifeblood that sustains every subsequent action, setting the financial boundaries within which everyone else must operate. With funding secured, the project moves into the hands of the contractors and engineers. Giant, multinational construction companies, specialized engineering consultants, local subcontractors. They are the builders. They turn designs into reality. They pour the concrete, erect the steel, and solve the thousands of technical problems that arise on site. The relationship between the project sponsors and the contractors is governed by complex legal agreements that detail what will be built, by when, and for how much. This contractual interface is a critical junction where information, risk, and financial incentives collide, often in ways that are not immediately obvious. Overseeing this entire process are the regulators and oversight bodies, environmental agencies, safety commissions, zoning boards, auditing offices. Their mandate is not to build the project but to ensure it complies with the law, meets safety standards, protects the public interest, and adheres to its stated budget and timeline. They act as external checks on the system, holding the power to grant permits, conduct inspections, and even halt work if necessary. Finally, at the end of the entire chain are the end users, the commuters, residents, and businesses who will ultimately interact with the finished infrastructure. Though they have the least direct control during construction, their needs and behaviors are the ultimate justification for the project's existence. They matter most in the end. When we first look for reasons why projects exceed their budgets, the most immediate explanation is the initial estimate itself. Animated bell curve, initial estimate low, final cost higher. This often stems from optimism bias, a well-documented cognitive tendency to be overly positive about outcomes. Planners and sponsors, genuinely enthusiastic, systematically underestimate the time, costs, risks. They focus on the best case, smooth progress, quick approvals, no surprises, not malicious, a human blind spot, even for seasoned pros. Early planning compounds this optimism. In conception and feasibility, the project is only an idea, a blank slate, unburdened by messy realities, geology, politics, logistics. Estimates come from high-level designs comparisons to past projects, reference class forecasting, but each mega-project is unique, location, new tech, political climate. Relying on past averages without specific adjustments seeds inaccuracy. You now have to deal with the unpredictability of the Earth. Beyond the flaws in initial planning, a second category of common explanations for cost overruns lies buried in the ground itself, Infrastructure projects are fundamentally an intervention into the natural world, and the Earth is rarely as uniform or predictable as our geological models suggest. During construction, crews might encounter unexpected ground conditions that were not or could not be fully identified during the initial survey phase. This can include anything from pockets of soft, unstable soil that require extensive reinforcement, massive, unmapped bedrock formations that are far more difficult and time-consuming to excavate than anticipated. These geological surprises are a classic source of delays and escalating costs. For example, a tunneling project might run into an underground river that was not detected by boreholes, requiring a complete redesign of the waterproofing and drainage systems. A foundation for a bridge pier might hit a patch of contaminated soil from a long-forgotten industrial site, triggering a costly and lengthy environmental remediation process that was never part of the original scope. They are encounters with the inherent uncertainty and hidden complexity of the subsurface environment. Even with modern geological surveying techniques like ground-penetrating radar and extensive core sampling, it is impossible to create a perfect, three-dimensional map of everything that lies beneath the surface along a multi-kilometer route. The Earth always holds surprises. Now let's have a look at the human element, errors and delays. Another frequently cited cause of cost overruns is the simple fact of human error and mismanagement during the construction phase. Building a massive piece of infrastructure is an act of immense logistical complexity, involving thousands of people and millions of individual tasks. In such an environment, mistakes are statistically inevitable. A surveying error of a few centimeters can lead to components that don't fit together. A misinterpretation of a blueprint can result in a section of a structure being built incorrectly, necessitating costly demolition and reconstruction. These are not systemic flaws, but rather isolated failures in execution that can have disproportionately large financial consequences. These direct errors are compounded by issues of coordination and communication. A large project site is a network of dozens, sometimes hundreds, of different subcontractors. If one subcontractor falls behind schedule, it can create a domino effect, idling other teams who are waiting to start their portion of the work. External forces, particularly those in the political and social spheres, introduce another significant source of delay, can result in a court-ordered injunction, halting all construction for months or even years while the legal process plays out. Or even attempt to alter the project's design midstream to align with a new political agenda. Time, in the world of megaprojects, is money in its most literal sense. Staff salaries, equipment rentals, site security, insurance, and loan interest. When delays push the completion date out by months or years, these costs add up relentlessly. They are often just triggers for the far more expensive and corrosive effect of time itself. These surface causes are real, but they hint at a deeper system that allows them to have such a powerful financial impact. The principal-agent dilemma. In any project, the sponsor, the principal, hires a contractor, the agent, to perform the work. In a perfect world, the agent would act entirely in the principal's best interest, which is to complete the project on time and on budget. However, the agent has its own interests, primarily to maximize its own profit. This misalignment is a hidden driver of behavior. This information asymmetry is a key source of systemic friction. A common contract type is the cost-plus agreement, where the contractor is paid for incurred costs plus an additional fee for profit. Since the contractor's profit is often a percentage of the total cost, higher project costs can lead to higher absolute profit for the contractor. This doesn't mean contractors are actively trying to inflate costs, but it does mean they have little financial motivation to aggressively control them. More importantly, they will scrutinize the project's initial specifications for any ambiguity or omission. When an inevitable change is needed, something not explicitly detailed in the original contract, the contractor can issue a change order. The fixed price becomes a floor, not a ceiling. This isn't a matter of good or bad actors. It is a structural flaw in the relationship, the unbelievable power of optimistic bias. Planners look at the history of overruns on similar projects and subconsciously conclude, this time will be different. We are smarter, our technology is better, and our team is more capable. This allows them to systematically discount risks, even when historical data suggests they should be paying them close attention. A project manager might face a choice between using a tried-and-true construction method or a new, innovative technique that promises to be faster and cheaper. The optimistic bias leads them to overestimate the likelihood of the new technique working perfectly and underestimate the potential for unforeseen complications. When these new methods run into trouble, the resulting delays and rework add significant costs. When leaders and champions of a project exude confidence and downplay risks, they create a culture where raising concerns is discouraged. This phenomenon, known as groupthink, leads to a collective blindness to potential problems. Each of these small, optimistically biased decisions eats away at the project's resilience. When a problem inevitably occurs, there is no buffer to absorb it, forcing a crisis response that is always more expensive than proactive planning would have been. Now, let's look at the change order feedback loop. The loop begins with an initial estimate that is often unrealistically low due to that low bid helps the project get approved and helps a contractor win the work. The first turn of the loop occurs when reality inevitably intrudes. That gives them significant leverage in negotiating the price for the new work, creating a cascade of subsequent change orders. Managing this constant stream of changes consumes enormous time and administrative resources. For the contractor, change orders can be a primary source of profit. It's politically easier to approve a series of unforeseen additional costs. The change order process thus becomes a hidden subsidy. The slow cycle of funding and risk. Instead, funding is typically allocated in stages, tied to annual government budgets. The thinking is that once a project has broken ground and spent a significant amount of money, it becomes too big to fail. This leads to a rush to construction, where projects move forward with unresolved design issues. This introduces a temporal gap between the identification of a risk and the ability to pay to mitigate it. The project must then be halted or slowed down while managers go back to the government or investors to plead for emergency funding. The slow, bureaucratic rhythm of public finance is fundamentally out of sync with the immediate real-world demands of a complex construction site. When a single megaproject consumes billions more than planned, the consequences ripple far beyond its own construction site. This phenomenon is known as the crowding out effect, repairing schools, upgrading the water system, funding public health initiatives. Maintenance is indefinitely deferred. The legacy is often decaying infrastructure surrounding a single gleaming asset. Crowding out also distorts labor and materials markets regionally. Smaller projects face higher labor costs and material shortages. Now, here comes the decay of public trust. Each time a project's budget balloons from a promised figure to a final cost several times higher, it reinforces a narrative of government incompetence and broken promises. The reaction is one of cynicism and frustration. The public begins to assume that all official cost estimates are fictions designed to win initial approval. When planners and politicians come forward with a new proposal, no matter how well conceived or necessary, they face an immediate credibility gap. Projects that are genuinely vital for a region's long-term prosperity may stall for years or be rejected outright. The sponsors can blame the contractors can blame unforeseen conditions, politicians can blame the previous administration that approved the project. This cycle of blame shifting prevents any real learning or systemic reform from taking place. This creates a vicious cycle. Distorted futures. How overruns shape what we build next. This is a phenomenon known as risk aversion being baked into the planning process. This leads to a future where we may build the wrong things simply because their costs are easier to predict. Not to build a high-speed rail line, not to invest in a next-generation smart grid, not to construct a complex coastal defense system. It creates a more conservative, less innovative, and potentially less resilient future. Not through a conscious choice but as a systemic adaptation to a world where we have failed to master the art of predicting the cost of our own ambitions. Cost overruns are not simply the result of isolated mistakes or individual greed. They are the predictable output of a complex system. The planner needs a low number to get a vital project approved. The contractor needs to win the bid and then ensure profitability through the mechanisms available to them. The politician needs to see visible progress and avoid the political fallout of canceling a project in which millions have already been invested. Yet when combined, these locally rational choices create a globally irrational outcome, a system that systematically undermines its own financial foundations and betrays its initial promises to the public. The unresolved tension, transparency versus momentum. On one hand, we could pursue a path of radical transparency. This would involve developing more honest, risk-adjusted initial budgets. However, this path carries its own significant risk. A project presented with a brutally honest and therefore much higher initial cost estimate may never get off the ground. On the other hand, we could accept the current system as a necessary fiction. We could acknowledge that the low initial estimate is a kind of political lubricant. This approach prioritizes action over perfect foresight, accepting that getting important things built sometimes requires a degree of initial subterfuge. Do we demand a level of honesty that may prevent us from building the future we need? Or do we accept a system that relies on a degree of initial deception to achieve its goals at the cost of public trust and financial discipline? There is no easy answer. Share your ideas below. It is the final, hidden calculation in the complex mathematics of our own ambition. You've been watching System Atlas, exploring how the world's systems really work.